Welcome back. So, today is our 12th lecture, and in this lecture actually in the previous lecture we developed Simulink model for buck as well as boost converter, buck converter, where we have also shown how to incorporate discontinuous conduction mode. So, now we are assuming that using the same method you can build such buck and boost converter Simulink model, but now we want to create multiple test cases. So, in this lecture I want to show like instead of, because such test cases will be very difficult to execute by running in Simulink, but we want to make such interactive case study from the MATLAB script file itself. So, we want to run Simulink in using script file, we want to process data and we want to create multiple transient scenario, customize them, then we can various things we can do more interactive. In fact, we can speed up the simulation by running through script file. So, Simulink and script file interactive simulation, then creation of various transient test cases, then fixed frequency and variable frequency modulation I want to show in this lecture. So, this block I am showing this particular block, actually we have shown this block in the previous lecture, that means this how to build this buck converter block, and we will use that block to move further. For today lecture we have taken a separate inductor resistance value, and I will discuss that how did we arrive such parameter value like inductor capacitor value, and here we are talking about a switching frequency of FSW, target frequency of 500 kilohertz. So, that's why time is 2 microsecond. So, in the subsequent lecture, maybe the next lecture in the third week, we will show that summarize whatever we have derived, various RMS current, ripple current, output voltage ripple. So, using those ripple criteria, how to select inductor capacitor value for a given switching frequency. So, those part we will discuss, but today we are taking it for granted that all this inductor capacitor, these things are given. And we are talking about some 12 to 1 volt. So, that means we are talking about 12 volt to 1 volt POL, which is a buck converter, that we are going to consider in today's class. We will also consider a boost converter, where the inductor is 1 microhenry, capacitor is 47 microfarad. All these parameter again we will discuss this selection of inductor capacitor in the next lecture. And here we are talking about a 3.3 volt to 5 volt, which is a boost converter, simply boost converter, because we are stepping up the input voltage. So, output voltage is higher than the input voltage, and we need to define here what is the maximum load current, I0 max. But if you look at two cases, in the first case we are talking about a conventional buck converter, and as I said in the Simulink we can actually use a synchronous buck by changing the DCM enable logic, and we also want to modify the diode drop as well, because in synchronous buck there is no diode and there is no question of diode drop. In boost converter we are talking about a synchronous boost, but you can also take a conventional boost, it does not matter. Why we are talking about synchronous boost? Because we want to see the dynamics of boost converter in continuous conduction mode, and we want to see what happened, what is the effect of right half plane 0 and so on. So, with this we will start our simulation. First we will run the open loop simulation. Okay. So, let us go to the open loop simulation. So, in this simulation we have considered this parameter which I have shown, 0.5, inductor 0.5 microfarad, capacitor is 200 microfarad, then time period is 2 microsecond, RL, that is the DCR of the inductor, then diode resistance, diode voltage drop, then MOSFET on resistance. MOSFET of the low side we are not using, so this is still there. 3 milliohm resistance for the ESR, 12 volt input and 3 point. So, here we are talking about 1 volt output, not 3.3, 1 volt output, and load current can vary. So, these are like we need to define all this in the custom Simulink file, all this initial condition, everything will create a test case. So, first if we run this, we know that the parameters are executed and these are all stored in this workspace. So, you can see this workspace. Now, we are going to Simulink file. So, in this Simulink file, we have set DCM enable logic to be 0. That means, we are not going to talk about, it is just we are trying to operate in continuous conduction mode. We are trying to operate in continuous conduction mode. Sorry. Yeah, continuous conduction mode. And this load resistance here we have set as 1 ohm. I have taken a clock for time period t, and which is nothing but our switching time period of 2 microsecond, and duty ratio d I set, which is Vref. So, if you execute this command, what is d? You can check d, we got 0.0833 because we are talking about 1 by 12 volt, this value. Next, DCM enable 0, input voltage 12 volt, load resistance 1. Now, we want to run the simulation. If we run the simulation, so this is starting from 0, all initial condition initially was 0. So, inductor current start from 0, output voltage start from 0. So, what we are showing here, the first scope is our inductor current, the second scope is our capacitor voltage. If we look at what are there, second is the capacitor voltage, third is the output voltage, and the fourth is the our switching clock. Okay. And we also saw in the previous class that if we want to store this data into workspace, then we have stored in the name of a result, which is a structure, and we can see that structure in the workspace, that is the structure, and which is a time vector as well as signal. Okay. So, we have 4 channels are there. So, each channel if you click, then you will get one by one data. Now, we want to create a text file, because instead of running the Simulink every time, we have a parameter file, and we can in fact customize some of the parameter during the run time, that is also possible. So, here what we will do, first we will clear the screen, close all. So, this will close all these workspace, sorry, all the figures and everything, then clear, it will clear all the workspace, and this will clear the command prompt. So, if you execute these 3, then what will happen, everything is now clear. Now, we want to call the simulation the parameter file, because if you want to run this through simulation, this .m file, we need to call this parameter file, and this can be simply called just by the file name. If you copy this, you can simply call this file name, that is it. Once you run it, then you can see all the parameters are again loaded. So, that means we are executing this parameter file. So, as a result, all parameters are stored. Next, what is our next task? So, after clearing this, we have executed this parameter file. Now, you can customize the initial condition, everything separately here, that will do. But before that, we want to first see the scope result. So, let us run again this simulation, because we have cleared everything. So, now it is running. Now, we want to take this data into our, it is there in the workspace. So, we want to create t equal to result, that is our vector that we have discussed, that in the structure consists of one time vector. The other signals structure, again each signal structure have a different values like different channel. Then we want to see what is the inductor current. So, inductor current is our, it is in which channel? Result dot signals, because if you click the result, you will see the signals, and inside signal if you go, the first channel, if you look at this, the first channel inductor current, then capacitor voltage, then output voltage, then the gate signal. Okay. So, let us go back. The first is the our inductor current, and if you look at this one, this result dot signal 1 dot values. So, this is what we have to type, signals 1 dot values. Okay. If we execute these two, just these two particular line, then we can plot t comma IL, the inductor current we can plot. Yeah, this is a plot. So, now we can plot, we can actually create a grid here, and we can see what are the current waveform, inductor current waveform, and so on. So, this is our inductor current waveform of a buck converter, because the duty is very low. Okay. So, you can call this waveform. So, by that way we can call like V cap, V capacitor voltage. Again we have to only change this channel, everything is same, the second channel which is 2, number 2. Then we want to show output voltage, it is in the third channel, and then we want to see gate signal QG, Q gate, QG, it is in the fourth channel. So, we got, now if we execute we can get all the data, but since you know, if we close the whole thing, then it will actually close all the data. So, we will not execute this for the time being, because if we execute, so this data are now stored. Now, we can use plot command. So, plot, but if you want to create multiple figures, then you can name like a figure 1 for inductor current, you can use plot t comma IL, we can use a different color, specific color you can use, then you can hold on, we can grid it, and so on. Then you can copy paste for the other waveform, figure 2 we can draw capacitor voltage, which is our V cap, then we can make figure 3, which will be my output voltage, and then we can plot figure 4, which is my gate signal, QG, that is it. Now, all these 4 channels can be, you can see all the 4 channels here, right. So, this is my inductor current, which I have already shown. Then you can see this output voltage, this is the capacitor voltage, and if you notice the capacitor voltage ripple looks like this, capacitor voltage, and then the other channel is the third channel is the output voltage. So, this is my output voltage, okay, output voltage, and then the other one is the fourth one is the gate signal. So, this is my gate signal, I can just take a portion of this and just show, yeah, this is my gate signal. And if you see that the gate signal, because the pulse width is very low, it is 12 volt to 1 volt, so it is a low duty ratio. So, these things are now possible that we can draw it. Now, after doing all this, the next question we want to create a transient case. That means we want to change the simulation time. Instead of 1 millisecond, we want to run it 2 millisecond like this. So we have to go and check it, right? But why do you check it? I can call this simulation time by tsim, okay, but you have to define what is tsim. So I can run this tsim for 2 millisecond duration, okay, it will run. Once it will execute, that means, but you have only set tsim, so you have to physically run it. So it will run for 2 millisecond now, right? Then how do I change the resistance value? Okay, next question. Now doing all these things, you have to go back and forth to Simulink file, do changes, check there, take the values. Why should you do that? First of all, if you want to plot in the Simulink, that itself will take time, because Simulink plot while it is running and plotting together, it will actually takes more time. It will actually take more time than if you run it and plot it after the simulation is over. You can store it. So this is possible. Now that means what should we do next? Solve this figure plot. So what we discuss first, we can customize this thing, the simulation time. We can call the results separately and then we can plot. But once we enable this block, then you cannot run, because now it close everything. So you have to again go back and run the simulation, otherwise the data are not. So you have to run the simulation, and that itself is a cumbersome job. So why should I do that? So to save that, I should call the simulation right from my .m file. That means I can just run open system, then I can run the Simulink file like this. You have to provide the Simulink file name. What is the Simulink file name? So this is the name of the Simulink file. So I am running this open loop buck converter, this XLS file. So I have to provide .slx. This is one. The next part, I need to simulate. I want to simulate calling from here itself. Now I don't have to go to my Simulink separately. So I can simply run it from here. It will run and again plot all this. That means now if I change my simulation time from 1 millisecond to 10 millisecond, my everything data, all this will be changed automatically. So it is running the simulation for 10 millisecond and plotting all this current waveform for 10 millisecond, which is 0.01. Okay, all right. So you can see the current waveform from here. You can check all this scope just by running simulation from here. That means what we learn? That means we can call the simulation file, Simulink file, from the script file. Okay. Even if you don't want to open, that is also fine. It will just run the simulation file and show the results. It will take some time to simulate and show the result. So all 4 results will be shown one by one. So you can enable or disable, doesn't matter. But my next task, that means I have customized my simulation time. I have called the parameter file separately at the beginning. I have called the Simulink file from here. I have run it. This is for executing the simulation. So that means when you call this, it will run the Simulink file just by executing this command. Then I have stored all the results like a time, inductor current, everything from here. Okay. And you have all this plot command, we can plot it. So maybe we do not need to plot all this. First 2 should be sufficient. We want to just plot output voltage and that is it. Yeah. So, only 2 plot is sufficient. So, it will call tsim is now running for 10 millisecond. So, if we want to speed up simulation, then we can decrease to 1 millisecond and run it again. So, you can do whatever we want. Nice. Now, why again we want to see all the time the Simulink file. If I just close it, it will not go to that screen, it will run it. Now, I have a next task. Why should I use, because we are calling the data into our workspace, then why do you need to again place a scope there? Because as I said, if you want to display the scope during live, like when it is running, it will actually slow down the simulation. So, we can in fact disconnect this scope, we do not need this scope at all, or maybe initially before you that I can use something like, if you go to the sync block in the library, there you will find something like a sim out block. I want to take the data to the workspace, so I do not need to pass through the scope, so that I do not want to display. But this sim out name can be changed, you can use sim out 1, 2, 3, whatever, it is your customized. So, I am just using default, okay, sim out buck, I call it, okay. So, sim out. Now, I can use simply buck, no problem, anything that you want, but it has only one input, whereas I need to take various signal data to the workspace. So, that means do you need multiple such sim out block, or we can use a vector input for the sim out, that is possible. So, if we have only one, let us say we have only inductor current. So, this is my inductor current. Now, what I am doing, I am taking this sim out and now I am just running it. If you run it, see in figure 1 you have plotted inductor current. This current is coming from the result block, which is connected to this particular scope. I want to check that sim out data of the inductor current should be identical. So, you go to sim out, this is also structure, the first is one time and the second is data, okay. So, first is time and the second is data. That means, even if you write what is my sim out, so that means I want to just type this particular name, okay, you just type it here, you will find the detailed description. So, it has a time vector and then it has a data element, okay. So, the time, that means if I write again T1, which is equal to sim out dot time, T1 is now created, and if I write let us say x1, which is sim out dot data. Since x1, since we are using only one like a scalar input, so it will directly give vector. Now, I want to plot, let us say I want to call the figure 1, okay. Then hold on, then I want to plot T1 comma x1 and I want to use a red color on that. Now, if you see both are exactly same, so you can't distinguish, both are like a blue and both are merged together. So, you can't identify that because they are the same data, same exactly same data. So, it is not possible, both are like overlap data, right. So, you can't distinguish them. That means, I do not need to use a scope to bypass the data. So, I can remove this scope completely. My next task is that sim out, I should not use a scalar, I want to use a vector. So, use a mux. So, let us use a mux. Now, once I use a multiplexer, that means it is muxing multiple signal together, so that you can take that data into workspace, multiple data at a time, you can take it to the workspace. Okay. So, before it loads, so let us go and check. Okay. So, what we have seen that parameter file, after parameter we will define something. In fact, you can specify a different input voltage, no problem. You can set it, and you can set a different duty ratio like a 1/15, okay, so that the different duty ratio in the Simulink file will be specified. Okay. Next, if we go to Simulink, let is we are waiting for the multiplexer to come. So, the duty ratio we can set VREF whatever we want, whether it is a parameter file does not matter. From the parameter file also we want to call this initialization file as well. This is one of the most important part that we should specify at the beginning, initial value. So, these are the initial value of the inductor current and the output voltage. Okay, so I can initialize from a separate point. Okay, let us go to the mux. So, I can take multiplexer, I can take 4 output multiplexer, okay, and it output is a vector. I can now connect to inductor current, capacitor voltage, output voltage and my gate signal. All these are possible now. Now, let us go back. So, if you run now the result is not there. So, we can't run this because we have eliminated the scope. Okay, we have eliminated the scope, but we need to plot it. Where is time vector and all this we need to plot it. So, how to get this time? It will show error because it does not have the time. Now, what is there? The same buck we have stored. Now, if you go inside, it has one time vector. That means, if I click here, that means if I write just a minute, SimBuck. So, SimBuck has one time vector and the data is a structure. That means, data has each data has 4 column and each column has many element that corresponds to the values of that particular signal at different time instant. Okay. So, that means now we are trying to do, we are first trying to create t equal to SimOut dot time and we are writing x SimOut dot data. So, this data will take, if you run these two, what you will first do, if you run these two, now if you go to x has 4 column, that means 4 column and each column you have data. Okay. So, we have extracted. Now, our inductor current is actually in the first column, it is the first column. So, x, so all the data in the first column will take, okay, row, all the row will take and the first column will take. Next, what are there? Inductor current, then capacitor voltage, cap, it will be the second column, then V0, it is the third column, and then QG, which is my fourth column. Now, once we do that, now we are ready and now we can draw the plot. Okay, so you can see now all the data are captured, the current and everything we got back just by, there is no scope anymore. So, that means there is no scope and you can speed up the simulation. Okay. So, we have created a transient case here. We may or may not open this block, does not matter, we can initialize here and we can define different parameters here. So, let us say voltage something here, buck parameter, we can define duty ratio. Now, if we change the bit ratio, let us say if we change the output to 3.3, we will see what happens. You run it. So, in the Simulink D, this should get changed. Yeah. So, okay, sorry, we should use Vref by phi, not this Vref by phi. That is the open loop bit ratio. Now you should run. Now the output voltage actually gets shifted, but it is not exactly 3.3 because there we have discussed that output voltage difference is due to the drop, because we have all considered the non-ideal resistor, inductor, capacitor, all this. So, inductor DCR drop, diode drop, then diode resistance drop, many things will contribute for this and mismatch in the output voltage. Okay. But yeah, at least we can run. Okay, the first thing. So, now we did it. Now, suppose we want to create another transient case. We do not want to run it now. Okay, we want to run it later. So, suppose after 1 millisecond, we want to run for another 1 millisecond, where suppose we have kept r equal to 1, r equal to 1. Now, here we want to set r equal to, we want to run for a different r, other parameters remain same. So, we are just changing this r value. That means, once these data are stored, now we want to run for another resistance. So, let us say we are going for 1 ohm resistance to 0.1. Let us say it is 1 volt, it is 12 volt. So, all this input voltage is 12 volt, output is desired is 1 volt. So, we set duty ratio as per open loop, but we can change it, and we set the initial load resistance to be 1 ohm, but now we want to make a load transient. So, the load resistance is changed from 1 ohm to 0.1, so that we can get a load current of how much. So, that means load resistance decreases, so current should increase. But now we can run again this simulation. That means, I can just call part 2 of the simulation, part 2. This is my part 1. This file will call once. Okay, this file I call one, part 1, part 1. If you want to change input voltage, fine. If you do not change, then you do not have to write it, because it is already stored, but we are changing these values, part 2. So, let us say we are running for 2 milliseconds, but one thing you will notice that now the inductor current, we are running for the next, we have already run for 1 millisecond, we have to run for another 2 millisecond. We cannot run from the same initial condition 0, because the already system has reached to certain level. Okay, so let us draw this. So, let us say the output voltage reached here some value. So, we have to take, or inductor current has reached some value, whether it is positive, negative, but it is at the final value, it is not 0. So, we have to start from this point rather than another 0 point. How to do that? That means, we have to take the final value of the previous simulation as the initial value of the next simulation. So, what is the final value of the previous simulation? So, you need to identify what is the vector length of this, any of all these vectors are identical length, and it is clear that if you look at this, it is like a 28,887, but that can vary. So, I can simply write m, which is a LEN length of any of this signal. I can use IL for example. If I execute this, it will show the length of this vector, and what is my m? Like a 28,887. So, we have to use this data as the initial condition. That means, what is the initial condition for the next simulation? it is the final condition for this. So, if I search for I underscore L, okay, M, then what is this value? Minus 1.413. And if you look at this waveform, sorry, actually where is my scope result? If you just run it, you will find the final value of this inductor current. If you go and go, this is what exactly it is showing, that minus 1.413. So, that is showing here minus 1. So, that is my final value. That means, first of all, that means we need to identify the final value. So, this initial condition will be my IL comma M, and this initial condition will be my V cap comma M. Okay. So, now you are ready to go. Now, I want to run, I want to hold on this waveform. So, this simulation as if is created. Okay. So, part 1, let us say we are running this output to voltages, where it is under part 1, that part 1 I am plotting all this, holding the value. Now, what I am doing, I am again calling this function, sim function, and doing this exercise. Okay, doing this exercise, sim. Now, for this I set the initial condition, I have only changed the load resistance, I am calling everything, and again I can plot this. Now, all will be overwritten, all this data overwritten, and now I plot is a red one. So, let us run the simulation. If you run, you will find the initial value of this is updated accordingly. What is the initial value? It is around 0.47, and what is the final value here? It is around, sorry, what I am showing, sorry. So, the final condition here, that means this is my initial condition, initial condition. So, red one, if you see the final initial condition that we discuss, minus 41 that value, and so it's fine. So, that means we can see some drop, that means if we run again, so we will check there is some drop in the output voltage final value is around 0.4825, whereas the initial value of the next simulation is something different. Another thing you will notice, the time shift, as if there again the simulation is running from 0 to T sim, So, we need to shift it, that means we have to shift to this axis. How to do that? So, in order to shift that, now we have to create the present time, which is right T1, it should be the previous time, which was my Tm vector plus. Why? Because this is a vector, time vector, but this time vector should we are adding an offset value. So, that the whole vector will be shifted by that time, and what is the offset value? That is the final time value in the previous simulation, that means T. So, if we write T m, so final time vector, because they have updated. So, let us do one thing in order to avoid any confusion. So, we will use this T1, 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 okay, we will run it again, everything is fine. Now, what is T? T is this. What is T1? T1 is this. What is T of m? This, m actually does not exist because it has updated the length. This length is no longer, this is the earlier length, m this is, let us say, M1, okay. Now we want to see what is my T of M, what is my T1 of M1, yeah. So, different value. So, now what we have to do, we have to add this offset Tm, okay, Tm plus, we have to add this offset. Okay. Now, if we add this offset, run it, now it shows that simulation time, the current also has changed, and two different color we can say that the transient actually scenario, and by that way you can simulate the load transient scenario, different transient scenario you can simulate here. Load has undergone some transient because we have changed the resistance value. And output voltage, the jump in the output voltage, whatever we can find from here, the output voltage there is a jump. This is due to the ESR, the ESR drop. This is a ESR drop. Okay. So, this ESR drop is, but now how to, because we are separately running, we have to combine together. So, we can combine together this X now. Inductor current, if we want to concatenate, that means we want to, so what is the T1 length? T1 like a M1 45,000, this is my T1, yes. So, I want to plot, I can plot together, I want to plot all these together. How can I do that? So, I do not want to plot here now, I want to plot together using a single. So, I just comment this. So, if I want, that means we want to create a structure, that matrix vector, earlier inductor current where it finish, then from there another column we will create. So, it will add together. How to do that? It's simple. Okay. Here time here will be T, that means I have to create this T, this, then T1. Okay. This is my new TIL will be previous IL, then this is called concatenation, I can do it, concatenate. Then here I can use V cap, that means previous V cap plus this V cap will get concatenated. Then this V0 will get concatenated, and this one QG concatenated with this. After that we do not need, now we can plot the complete T, that means now we can plot T, and let us see. Now it shows the complete simulation, and it also joined that discontinuous line where we got some discontinuity. So, this was our point of discontinuity, because we have clubbed together both the simulation and they can run. So, we have created a case study where the inductor current also we have merged them together. That means, we learn that how to simulate a transient case study. This is in open loop, but we can do it in closed loop, there is no problem. Now, we will go to the Simulink block and changes. So, that means we can create transient case study and we can make simulation. So, we can now remove all this plot. So, part 2. So, we do not want to plot part 1, part 2 separately, we want to plot it together. Now, we can play with different simulation time, when do you want. So, all this we can do it. Now, we have to do closed loop control. So, load resistance we have changed, we can change even further down, we can run it. So, it will show, and you see that the simulation time is much faster, and if you run the same thing in Simulink, it might take more time, because you can save lot of simulation time here. Okay. So, now this I am showing. Now, the same file I am going for a closed loop. So, I will call it as a save as buck converter simulation, like a voltage mode control. Okay. So, in this voltage mode control simulation, I will use another file name VMC, but I have to make changes there. VMC. So, because we are using another Excel file, so you have to go and save as, here it should be VMC. Okay, now we have created a voltage mode control simulation environment, and we need to see the closed loop control. Okay, so far we have checked with the open loop. Now we have to go for closed loop. So, in closed loop, now we will not operate the gate signal using a fixed duty ratio. So, what are we going to do? Now, if we go back to our PPT, so we need to create something like this. That means trailing edge modulation, and in this modulation we want to use a control voltage, and we want to compare a sawtooth waveform. So, this sawtooth waveform we need to fix some upper and lower limit. Okay, this sawtooth waveform. So, where we call it as a Vmax. Okay, and we can start here, we can call it as a Vmin, and this is my time period T, I can set it. Okay, Vmax, T. Now, how to go? We want to go to simulation. Yes. So, before that, now we need to define. So, input voltage is given. I do not want to change, because you can, I just want to use this V in whatever I want. I did not need to use a separate duty ratio, because now I am going for closed loop control. And what we have to do first, that means we have to set some other parameter, which is my Vmax equal to, let us say 10 volt, Vmin is equal to 0. This is for RAM, and time period is already actually defined. So, time period is defined like a 2 microsecond. So, this is enough. Now, what next we have to do? Go to the library, sources, there you will find this sequence, periodic sequence, and if you go, the time will be T, it will from 0 to T, it will repeat, and it will change from Vmin to Vmax. Okay, but we are yet to set. What is next? That means initially, before we go to voltage mode control, we want to provide a control voltage, that means a constant quantity. Okay, constant quantity, and we want to use a comparator, that means commonly used block, there will be something like a relational operator. So, if the first output, this one, is smaller than the second, it will go high. That means, if my constant, which let us say I am setting like 5 volt, let us say I am using Vcon, I have to define what is Vcon. Vcon is smaller than this, okay, then smaller than this, then I will generate a get signal. So, we have not yet used the closed loop, but just we are generating where we need to define what is my Vcon. Vcon equal to 5 volt. Now, let us check what happened. Yes. Now, the output voltage has gone high. It is too high because we are using 50% duty ratio, but Vcon, what should be the Vcon? The control voltage, in order to achieve the duty ratio. So, let us say if we set 12 volt here, 12 volt and 1 volt. So, you can set Vcon to be 1 volt, then duty ratio will be accordingly generated. So, 12 to 1 volt, that means my shortwave waveform is going for 12, Vcon is, if you want to check the gate signal, okay, let us plot T comma QG gate. Yeah. So, if you take the gate signal, I want to see what happened actually. Maybe the logic is, yeah, it is a very low duty ratio, but then why low duty ratio? The QG, from where you are tapping the QG? Oh, we should tap from here. Okay, let us run it and for driving signal. Okay, maybe we need to put a scope, a driving signal. So, QG gate signal, okay, relational operator. Should it be, okay, let me check whether there is any logical change or not. Yeah, I think there was a change logical problem, because what was the initial logic? We said if Vcon is, it should be high when the Vcon is higher, but I took the reverse logic. Vcon, as long as Vcon is higher than sequence voltage, because if you go back to this waveform, as long as this Vcon, because if we set Vcon somewhere here, so it is higher, then it should give the on pulse. This is a Vcon, but we have not yet incorporated the latch circuit yet. Okay, so let me erase this part. Okay, now going back to our logical block. So, we have set a Vcon logic, but now this is not enough. That means it will be high when it will reach certain value. Now, we want to introduce our RS latch, that means latch circuit. So, that flip flop. So, RS flip flop we want to introduce, and this RF flip flop, because we want to implement our trailing edge modulation technique. What is the set pulse for this flip flop? The set pulse for this flip flop, again flip flop cannot take, there can be double, if you try to run it, because this is a double data type is a double, but it require a Boolean function. So, we need to set another such relational operator. That means, as long as this is higher than, greater than 0 or something like that. So, greater than 0, so it is greater than 0, it will be high. So, you can set like a 0.5, something like that. Yeah. So this is my set pulse, and here I can use just 1% because it is just edge. You require the clock edge. Okay, fine. This is my DCM, that is my constant. That means this is something like constant. And now I have to use the relational operator, and here it is used to reset. That means we have to reverse the logic. As long as V1 is above, it should be high. So we should now reverse the logic, because in order to operate this, now we can start the simulation and check. Yes, same thing is happening. We just, so this is like our controller, where we have not yet used a closed loop control, we are just using. Now this control can be modified by placing a error voltage. That means we need to consider one, the traditional block feedback, like feedback logic. So this is my feedback logic, and this output will not go directly. So we need to this one plus, other is minus, sorry. Okay. So there we are connecting the output voltage directly, and here we are setting another constant which is called as a Vref. So there we are setting Vref. This is my reference voltage now. Now this is my like a standard classical feedback control, and we want to use a gain. Simply proportional control, maybe you can use some gain of 100. So I can gain something like Kp, and this Kp I can now define like Kp equal to maybe 50. So now let us run it and see what happens. So once we add proportional control, then we can see that the transient response is now, the nature of transient response got changed. The nature of transient response got changed. So it's a step up transient, but it is just a simple proportional control. So now we can add more complex PID control and so on. We can do that. So that means we created a transient case study. In the part 2, we have changed the load resistance, and so if we want to increase the proportional controller gain, let us say 80, how does it look like? It has further improved the performance, but there are limits, that there is a steady state error in the output voltage, and you can also see during transient the startup logic is something which is unacceptable. The output voltage reaches 3 volt, which is not at all acceptable. And if you see current is reaching 80 volt, 80 ampere, which is again like unacceptable. So this kind of, we need to do something different in order to enable this startup operation. Okay, but at least we have learned how to run this simulation, and we can do the same exercise for the boost converter also. But in today class, I want to limit, we can create such multiple transient case study we can create, and we can keep on adding. For example, I want to again go for third step down transient. So what I will do, part 3, now we go back to, let us say, around 1 ampere, 1 ohm, maybe this time we change simulation time. it will again take, but now we have to call what is my m, and m is my again length of IL. Length, and again it will update all these value, and again it will take what was my previous t, and accordingly it will update, and we want to plot after. So, now we want to plot like a, this time like a green plot, we want to do green, or maybe sorry, the whole entire plot. So, let us see what happen if we do step up and step down transient. So, now you can see the whole step up and step down. This was the step up transient, is a step down transient, huge overshoot. The current also undergoes like a step up and step down transient. So, you can create such multiple test cases using Simulink, but we do not need to go physically change the variable, create adding multiple switch and all these block we can actually insert inside one's subsystem. We do not need to do that. In fact, what we can do another case, for example, we change load. Now, we do not want to change load, we keep R equal to let us say 0.0, 0.1, but we want to change the input voltage. It was 12 volt, now we just want to change Vin to 8 volt, again Vin to 15 volt, and run it and see what happens. Yes. So, you can see there is not much effect, this is a supply transient we have made, and current also has not changed drastically. So, these are possible, all these you can run it. And the third one, which probably we want to see, it will be 1 volt coming back. I want to make Vref equal to 1.1. Okay. So, we want to see what happened. Yes. So, we can create a reference voltage transient. There is a huge overshoot and undershoot, which is not acceptable. There can be huge current overshoot. So, we need to reduce the gain and we can check, but this is just proportional control. So, now finally, we can consider a controller, which is not simply proportional controller. So, we can consider let us say a PID controller. You can plug in a PID controller, we can use it, all this PID controller, and here you can use Kp, Ki, Kp, Ki, Kd. The controller gain you can plug in here, and you can accordingly create Kp equal to this, then Ki equal to maybe 10,000, and initially we are taking Kd equal to 0. Now, you can run it. So, this we can create transient simulation case study, and here we can again change the load resistance. We have to see the load transient R equal to 1 ohm, R equal to and so on. So, we can see the controller effect. Load transient scenario, step up, step down transient. So, with this actually we can implement various types of logic. Setting the control voltage, we can accordingly set the desired value that we have discussed earlier. We can do constant on time control, but today I am not going to demonstrate constant on time, because we will implement this constant on time in a subsequent lecture where we will have a dedicated variable frequency control method, where we will have a constant on time block, and we will also use this for light load control. So, this block will be implemented in the subsequent lecture. So, today we just wanted to show that the Simulink model development for fixed frequency, we have not yet gone to the variable frequency, that we have kept it for the subsequent class, and we have shown the interactive case study of a buck converter, and we already have a built in model for boost. So, we can do it. That means, using custom MATLAB simulation, we can call the Simulink file, we do not have to run it through Simulink scope, and you can directly run through MATLAB file, and you can speed up the simulation, and you can create multiple transient case study. So, with this we want to finish this lecture. Thank you very much.